All right, this last segment gets at a little more general question, which is, um, should I use kinetic or equilibrium modeling? Which one do I want to assume? And we know that with kinetic expressions, you may need to have small time steps. With equilibrium, you can use the predictor-corrector method and get some larger time steps. Even if you wind up iterating instead of doing predictor-corrector, this is actually a little easier. You can take time step size of sort of arbitrary size as opposed to be limited by this kinetic expression. In this case, your time steps would be limited more by the advection rate, right? How fast your water, the concentrations are moving, instead of how fast the reaction is proceeding. So there, if you can do this, sometimes this can be helpful. All right. So this is, I'm rewording that question. Does the local equilibrium assumption, that's LEA, does it apply? Okay. Obviously, that depends on the speed of the reaction. It depends on your time scale of interest, right? So speed of the reaction relative to your time scale of interest. If you're talking about millions of years, then boy, calcite dissolution is an equilibrium reaction. If you're interested in milliseconds, well, you might have to consider kinetics then for calcite dissolution. Okay, but this also depends on the speed of the reaction compared to advection. All right, so you always hear about the example of sharks; they have to keep moving. All right, and that's because your reaction rate, you can't react as fast. If you hold still, you could deplete the oxygen in your gills, I guess, your gill system. All right, if you keep moving, you constantly get a fresh supply of oxygen-rich seawater flowing through your gills. All right, so that's a very physical example of when advection versus reaction really matters. Okay, so so let's think about that. We have a way, you already know about the Peclet number, all right, which told us something about the rate of advection versus the rate of dispersion. So you might not be surprised to find out there are tons of these dimensionless numbers. They're pretty cool. This is the Damkohler number, and it compares the reaction rate to the rate of the advective flux. Okay, so your reaction rate is this is what you'd expect. There's the reaction rate of the kth species. Your eta here is the stoichiometric coefficient for that component in the kth reaction. Okay, for that kth species, the kth reaction, I mean. You have another length scale of interest, just the way we did in the Peclet number, and that's how you get these to be dimensionless. All right, and so this is overall the reaction rate, how fast this is going to change with time due to the reaction. All right, and this guy here is the equilibrium concentration of the ith species. All right, so if you were at equilibrium, this is what its concentration would be, and here's the advection rate. Okay, so this is a kind of an interesting number. Let me show you what you can do with it. Okay, using the Damkohler number and the Peclet number, you can develop a dimensionless equilibration time. All right, so that can tell you, is it fast enough that we can simulate it as an equilibrium reaction? But these aren't easy to calculate, or I mean, they aren't that hard to calculate, but they aren't that easy to interpret. I mean, what's a dimensionless equilibration time of 2? Oh no. But let's look at, well, we'll talk about it in a minute. We have a way to convert this into a real equilibration time. But just double check the ends of these axes. Here's fast reactions. Here's fast advection. All right, and here is a large dispersivity, and here is a large scale of interest, or large advection in the Peclet number. Okay, so Peclet, Damkohler. All right. And just to remind you that the Damkohler number, if the log of the Damkohler number is 0, that means the Damkohler number is 1. So this going across here is the cutoff between fast reactions and fast advection. All right, so if you want to use equilibrium reactions, you want to be in the upper part of this graph, and then you can think about where you are in here. All right, so let's see the next one of these guys. Now, here is the actual equilibration time. You multiply this tau, which is what you're reading off this graph, by your length scale of interest and divide by your advection rate. All right, I've marked the Damkohler number equals 1 right here. And this is, the Peclet number is 2. So if you're thinking about numerical issues, then this is the side you want to be on to not have issues with oscillations. All right. So this is an area where you'd probably want to be if you wanted to be simulating equilibrium reactions. And otherwise, you'd be down here somewhere where you would be thinking more about kinetic reactions. But this is really, it's fun to just calculate this number and say, oh, what is my equilibration time? Is it 5,000 years? Is it 5 million years? Is it 5 minutes? Right? So anyway, these are ways you can tell what approach you should be taking.